Hi everyone, so today we're going to look at the final topic that we have to cover, which is power factor and power factor correction. So at the end of the session you should be able to calculate power factor in the AC circuits, explain why power factor correction is important, describe the principle of power factor correction, and calculate capacitance values required for power factor correction of inductive loads. So just to summarize some of the equations that we did before, you should now know some of the basics, like in phasor notation we have V is equal to I Z, and notice the bars across all of them over the top because they're all phasor quantities. So just like you denote a vector, you denote the phasor the same way to show that it has both a magnitude and an angle. Then we have S is equal to VI conjugate. And remember, this was just like P when we have in DC circuits, P is equal to VI. Here we have S is equal to VI conjugate, which reduces to P is equal to VI if the frequency is 0, because then I would be equal to I conjugate and S would be equal to P. Now I could combine both of these as well and say I wanted to find an equation with S and V and Z, just like I have P is equal to V squared on Z and P is equal to I squared R. I could do the same thing with S. So if I substitute in here for V is equal to IZ, I will get S is equal to I by I conjugate by Z. Now if I look at I and I conjugate, when I multiply I and I conjugate, if this is I here, I conjugate will be down here. So when I multiply these together, remember the angles add. So when I add this angle to this angle, it would end up being an angle of 0. And the magnitudes would multiply. So I would end up getting a vector of angle 0 and magnitude I squared. So this would work out to be S is equal to the magnitude of I squared by Z. Z is still a phasor component, it's still a complex value. So you would get an angle, you would get the correct angle on S. And similarly, if I work it out with V, if I say S is equal to, I substitute this time for I and I will have V on Z, I will get V multiplied by V on Z conjugate. Then that would give me V multiplied by V conjugate would be magnitude of V squared over Z conjugate. So these are all different things I could use. So, and these are all things you should keep in mind as we proceed to the next section. So let's look back at the power triangle. So if you remember the power triangle, we have P, which is represented on the horizontal, Q on the vertical, and the hypotenuse is S. P being the real power in watts, Q being the reactive power in VARs, and S being the apparent power in VA. So now the power factor is defined as the ratio of the real power to the apparent power, which is P on S. Now if we look at the triangle, the P on S, and we take P on S, this is the same as the cosine of the angle between them. And this is what we would look at as power factor most of the times, the cosine of the angle between S and P. This also happens to be, this angle is also the same as the angle between the voltage and the current, theta V minus theta I, the phase voltage and the phase current. So this angle here is the angle between V phase and I phase. And that's an important thing to remember when you get into three-phase systems next term. When you look at line voltages and phase voltages, the angle here you look at is always the phase voltage angle. Good. So the important thing here to remember, just to recap, is that the power factor is the ratio of real to apparent power, and that is the same as the cosine of the angle between S and P, or V and I. So why is this important? Why do we want to find out about the power factor? So utilities typically only bill customers on the real power because that is the power that is actually being consumed. Remember, we talked about reactive power circulating through the system. So the generators must still produce apparent power, and this is problematic because the more reactive power you produce, it means more current is in the line, and that will turn into more losses, and you'll see that when we do some examples. So it is desirable to keep the real power close to the apparent power, and this will allow you to make money on everything you produce. You'll have a more efficient system with less losses. So to achieve this, since the thing that causes the poor power factor is the VARs in the system, which comes from the inductive and capacitive components, the thing we need to do is to reduce the amount of VARs in the system, reduce the net amount of VARs in the system. Typically, we have an inductive system. We have lots of motors in industry. We have lots of transformers on the system, and these all have they all store energy in magnetic fields, so they all are inductive. So we have positive Q, or what we call a lagging power factor. So to compensate for this, what we typically do is we add capacitive Q. We can't actually reduce the amount of inductive Q in the system easily, because that's what the devices need to work. So you can't remove it, because that would mean you're removing the device or redesigning the device altogether. So what we could do is we could add VARs into the system, but in the opposite direction. So we add capacitive VARs, and that has the effect of bringing down the net Q in the system. So that will allow us to have a higher power factor while still maintaining the same inductive load.